Hi, this is Miss Oliva, and I am going to go through 3.6, which is about application problems with exponential functions. So let's get started. Okay, so one of the questions in 3.6 is like this, where they're giving you this formula to find the average rate of return. So basically, we're trying to solve for R. Suppose $100,000 was from a retirement account is invested. So if this is how much you're investing, this is your P in a large cap stock fund. After 35 years, so that's the T, the value is $178,013.11. So if this is what you get at the end of the 35 years, then this is the A. So A is kind of your ending balance. P is what you put into the account to start with. E is an actual number, right? E is 2.71 something, something, something. So there's a button in your calculator for that. R is the interest rate. So we're trying to solve for that. Excuse me. And T is how many years. So you'll put this in for A, this in for P, times E raised to the R, which we don't know, times 35. So to solve this, since there's an E, the first thing I'm going to want to do is get that by itself, just like we were doing before. So divide by 100,000. So 178.13.11 divided by 100,000. Okay. So you get 1.780131, and that now equals E raised to the R times 35. So I need to get this exponent down. So I'm going to do ln of both sides, and that'll wipe that out. So I'll just keep this here for now. So that equals R times 35, or 35R. So my last step would be to divide by 35. So in my calculator, I'm going to do ln of this number divided by 35. Make sure if your calculator puts a parenthesis here, that you end the parenthesis before you divide by 35. Or else it would be a different problem. So I got 0.01647, etc. This is a percent though, so you would need to move the decimal twice to get the percent, and then see what they wanted you to round to. How long will it take the investment to reach $250,000? That's like $250,000. So that would be 250,000. Again, if we started by putting in 100,000, and now we know the rate, so I'm just going to put in this whole thing to keep it as accurate as possible. And this time we don't know the T. We're trying to find out how long would it take to do this. So again, we're going to divide first. So the 250,000 divided by 100,000. So that's 2.5. So basically the same steps, because now to get that down, I'm going to do ln of both sides, and it goes away. So ln 2.5 equals this. So, oh, I wrote it wrong. 0.016. Okay. So my last step is to divide. So ln 2.5, I'm going to end the parenthesis, divided by 0.01647. And they wanted us to round to 1/10 of a year. So 55.6 would be the time. So both of these were solved in the same way. Just one time we were trying to find the R, and then the other one we had the R and we're trying to find the T. Okay. Same type of equation here. P of T equals P sub 0, which means the initial population, times e to the k, which is like the rate, times t. So we're using this to model the population in millions, t years after the initial census. So first I'm going to do it for the Asian country. So if this is the population when t is 0, that is that P sub 0. But then this number is the population after 10 years. So when t is 10. So that would go over here. We don't know the k, but we know that we got that number after 10 years. So plug in 10 for the t, this number for the P of t, and this number for the original. How do we solve it? Same way. I'm going to divide by that 22.9. And then I'm going to take my ln. So if you ever have to write a number down, you're going to write as many numbers as you see until you get to the end, and then you'll round to whatever they asked you to round to. So right now we're here. Instead of k times 10, I'm just putting 10k. So now we will do the ln of both numbers. So it's best if you can keep this number in your calculator and now do ln of that answer. So if you can do that, that's great. If you can't do that, then you're writing down as many numbers as you can. So we'll get this, and then we'll divide by 10. Okay, and then round that to 5 decimals. Okay, so let's make sure we round to 5 decimal places. So 0.00343. Okay, so that's the same thing you would do for the South Pacific. It's just that the 19 is going to be your starting amount, and the 22.6 would go here. So you would do the exact same thing. All right, let's look at 3. Refer to this equation, which is very similar to what we've been doing, used for radiocarbon dating. At an archaeological site, scientists uncover human remains. A sample from a human bone taken from the site showed that 28.1% of the carbon-14 still remained. How old is the sample? So if we're using this equation to find how old T, we would need to know this and this. But we don't really know either of them, but we do know that the ending result is 28.1% of whatever it started with. So I'm just going to call it 0.281 times Q sub 0, because we don't know what that is, but we know this is 28.1% of it. So if I set it up like this, then when I divide by Q sub 0, like we normally would, but it would normally be a number, but in this case, they just wipe each other out. So now I have 0.281 equals E to all of this. So now we would do the ln part, and then we divide by that decimal. So your final answer is what you get when you do all of this. So again, make sure you do the ln 0.281, end your parenthesis, and then divide by the decimal. So I got this and just round to the nearest year. Okay, so if I got this 0.9, I would round that to 91. So it's that many years. Okay. Last one. This formula is a little different, and it's giving us the Canadian population since 1900. Remember, in problems that talk about years, they usually give you a starting year. And so that is your 0 as far as t. And so however many years since then is the t. So if I was talking about 1905, it would be 5. T would be 5. So first it's asking you to evaluate p sub 0. So that means plug in a 0 for t and make sure you're careful with your order of operations. So I got 5.3. And so that was the population in millions. So 5.3 million in 1990, because that's what 0 means in this problem. Okay. For B, it's now asking me to use the function to predict what's happening in 2020. Well, since 2020 is 120 years since 1990. Oh, whoops. I think I wrote this wrong. This is supposed to be 1900, sorry. Now it's 120 years, yeah. Since our T sub 0 was 1900, that's what we're comparing it to here and here. So now do you see that it's been 120 years if we're looking at 2020? So go back to your formula and plug in 120 for T. Again, be careful with your order of operations. Make sure you're doing all the stuff at the bottom first, and then 55.5 divided by what you get on the bottom. All right, and I got 38.0 million. Okay. And so if it wanted you to predict 2050, you would just plug in T equals 150. So I'm not going to do that one. But then when, so that means we're trying to find T, when would the population reach 50 million? Just means you set it equal to 50 and solve. This one is a little trickier to solve. So when you have a big fraction like this, the easiest way to start is multiply this fraction to the other side. But then we're going to need to distribute because we want to be able to get the t all by itself eventually. So I would distribute this to get 50 plus 470e to all of this equals 55.5. So my next step is to subtract the 50, and then I'm going to divide by the 470. So when I subtract the 50, I get 5.5. And now divide by 470. Equals this decimal. So I do ln of both sides and then divide. So my final answer is going to be ln of that decimal I just got divided by the negative 0.02515. So -0.0. Okay, and this is a mess, sorry, but I ended up getting 176.85. So depends on what they want you to round to. I didn't write it down, but if they want you to round to the nearest year, it would be 177. Okay. E and F are asking what numbers we're approaching when we go to infinity, basically. So if you take this equation and plug like 10 in for t, then 100 in for t, then 1,000 in for t, you'll see that your number is just getting smaller and smaller and smaller. So it must be approaching, meaning a very small decimal. The larger that t gets, you're getting a much smaller decimal. So that means it's approaching, but we'll probably never get to 0. And then limiting value of P of t means do the same type of thing, but go back to the original equation and plug in 10, plug in 100, plug in 1,000, see what's happening. And you will see that this time the number is getting closer and closer to that 55.5. So that is the limiting number. So you're just going to get closer and closer to that, but never quite get to it. Okay, that is it for 3.6. Good luck, and let me know if you have any more questions after this.